Welcome to lecture number 10. In today's lecture, we are going to see the concepts related to speculative execution. Last two lectures, our topic of discussion was dynamic scheduling, wherein instructions are reordered in order to improve the performance of instruction pipeline. As a specific case, we have seen how Tomasulo's algorithm is used to take care of operand forwarding, register renaming and handling of other hazards. One point which was put as a condition for the working of Tomasulo's algorithm was we cannot run instructions that are dependent on branches. So, instructions that come after a branch instructions cannot be executed on a Tomasulo's algorithm. But we have seen that control hazards also has to be handled in an instruction pipeline. Today's topic of dynamic instruction scheduling with speculative support will make you aware how speculative execution can be done or how can you run instructions which are dependent on branches. So, in the slide that is been shown, this is the general architecture which is used by the Tomasulo's algorithm, where you know that instructions are there in the instruction queue, and then we have different functional units, and these functional units are having reservation stations. So, during the issue stage you check for vacancy available in the reservation stations, and then the instructions are being issued into them. As and when the operands are available, then the instructions are taken from the reservation station and are carried out in this execution unit, and at the end of execution the results are pumped into common data bus, which will update the registers, which will update the memory if it is a store operation, and which will update the pending instructions waiting in the reservation station. We have seen that no instruction will initiate execution until all branches that precede it in the program order have completed. The reservation station associated with a functional unit is not free, it is considered as a structural hazard and issue will be blocked. Once the issue is blocked, all other pending instructions are also blocked. The Tomasulo's algorithm for loops. So, when you have loops, how do you run loop if no instruction will initiate execution until all branches that precede it in the program order have completed? So, this is a very tough condition to satisfy, because generally when you have a loop, we have seen it in compiler scheduling that the adjacent iterations of the loop is also unrolled, such that we are not waiting for the instructions in the previous iteration to complete. So, unrolling the loop is a very common approach that is used to improve the performance of instruction pipeline. But when in Tomasulo's algorithm, when you see that you cannot execute speculative instructions. So, what we can do is, here is the role of a branch predictor. You predict the branches are taken and issue instructions across multiple iterations. Since the first line blocks you in executing instructions that are after a branch instruction, which will stall the pipeline for some time until the branch instruction has been resolved, the second condition what is mentioned over here will permit us to predict that the branches will happen. If the branch is happening, we know what are the instructions that are to be executed, execute them across multiple iterations. So, consider the case we have a loop where we load a value and the value is coming to F0, you are going to multiply the content of F0 with F2, storing the result in F4 and storing the value back. And then we have two instructions that will manipulate the loop. You are going to subtract the value of R1 until the value of R1 reaches R2. In this case, if I am going to unroll the loop one more time, so you have a load, mul and store that is part of first iteration, and again load, mul and store that is part of the second iteration. Now, you can actually issue all these instructions, that is what is been shown across iterations, but only the first two loads may be executing. You are actually waiting for the load to complete. So, think of a case that you have two load store unit. The first load is carrying out in the first load store unit. The second load will be carried out in the second load store unit, but we are not sure whether the second load is actually required or not, because it depends on the condition of the branch. So, we are predicting what is the outcome of the branch, and then go and execute instructions that are generally coming after the branch condition is been resolved. So, in this scenario, the instructions mul and store that are part of first iteration are not yet complete, but an instruction that is load which is part of the second iteration can be executed. So, this kind of a mechanism requires some kind of an extra support. So, consider the same program loop that is been discussed now. We are loading a value, multiplying a constant to that loaded value, that is called f0 and f2 is been multiplied, and then you store the resultant back into the same location and then go to the next element. So, this is the register status indicator that is been shown in the conventional Tomasulo's algorithm. So, here the register status indicator is giving the status of 6 registers f0, f2, f4, f6, f8 and f10. Now, I will take you through a quick snapshot of what happens to the reservation station entries when you execute multiple iterations of this loop. So, what you see here in this table is your reservation station, where we have the operand value Vj and Vk will contain the operands if the operands are readily available, and Qj and Qk will tell you the functional units if operands are not available, and A will carry the address. I am going to talk about the very first load instruction is going to write the result into F0. So, register status indicator of F0 should be pointing to load 1, and the address is 0 plus content of R1, which will be carried out in the first load unit. Assume that you have 2 load units, 2 store units, 2 multiplication and division unit and 3 adders. Now, you are going to the multiplication instruction, wherein one of the operand is available in the register file. That is why your Vk value, which will have the second operand f2, but f0 is not available. Since your value of f0 is not available, I am specifying the functional unit that will produce. So, load 1 is going to produce a result that has to be returned to f0, and your multiplier unit is essentially waiting for an output to be produced by the load 1 unit. Moving further, for a store operation, imagine you have a store unit and his first operand is R1, which is used for computation of an address, and then it is waiting for a value that will be produced by the multiplier unit. So, this multiplier unit has to produce something, and then it has to be put in CDB for the store 1 unit to do. Now, these 2 instructions, that is the multiplication instruction and the store, are actually waiting, but we are going for a loop unrolling. So, you can see that since the multiplication operation is going to write the result to F4, the RSI, register status indicator of F4, points to multiplication of. Now, the second load operation, that is actually the first instruction of the next iteration, we know that this load for the second iteration will happen only if this branch condition is met. So, the branch condition tells that R1 and R2 value should be equal to 0. Now, when I predict the value of the branch, and if the prediction say that the branch will be taken, that means the control will be transferred to loop, wherein the load, mul and store will be executed for the next iteration. So, generally such an execution will happen only after the branch condition is resolved. Here we predict that the branch will happen, we are not waiting for the outcome of branch, we are going to the next iteration and trying to issue the instruction. Since you have one more load unit, I can issue the second load, but you can see that the value of R1 and the offset has to be appropriately adjusted. Generally, the value from which the reading happen is 0 plus content of R1, and now when you go to the next iteration, it will be content of R1 plus minus 8, because we are decrementing the value of R1 by minus 8. Now, moving further, the multiplication instruction, since I have 2 multiplier units, I can carry out the multiplication. So, the second multiplication unit is waiting for the output of load 2, whereas your first multiplication unit is waiting for the output of load 1. So, that is the dependency there, and this is the dependency there. So, if you have more number of functional units, I could carry out instructions across iterations and they all will wait for the appropriate values. Now, coming to the store instruction, The case of a store instruction, you can read when, since there is one more store unit, the store unit is in turn waiting for an output produced by the multiplier unit 2. And we have to see that now at this point F0 values and F4 register status values are updated to load 2 and mul 2 respectively. So, the second iteration, when you are going to execute the second iteration, the RSI value changes, and when you are going to execute the first iteration, the RSI value has a different set of index. Now, think of a case that your load instruction is going to get over. So, both load 1 and load 2 units will be free. So, the moment load 1 unit is free, then your multiplication instructions can actually start. And once multiplication is over, the corresponding stores will do. So, store 1 and store 2 essentially will complete the operation together, and then your instruction execution will continue in the normal fashion. So, it is kind of a speculation. We are predicting that the branch is happening. Now, can we execute instructions of adjacent iterations without knowing whether such an iteration will take place or not? Can you bypass control hazards? These are basically instructions with loading and storing that we have seen in this example. Let us try to understand, can I perform a load of the second iteration when the store of the first iteration is not yet over? We are trying to have a dynamic instruction execution, out of order execution. How much out of order is permitted and what are the consequences of out of order execution? This is known as load store order conflict. A load and a store can safely be done out of order provided they access different addresses. If a load and store access the same address, then either the load is before the store in the program order, like this. So, you are going to have a load of R1, 8 of R2, and let me take the second instruction. It is a store of R5, 8 of R2. Let me put up the third one, another load of R6, 8 of R2. So, if the load is before the store in the program order, let us say this is my load and store, where the load is before the store in program order, and if I try to interchange them, try to interchange means generally the program order means the load has to be over, you are loading a value and then you are going to store. That means after the load operation is over, some new value is returned to the location 8 of R2. So, when you interchange, that means when a store happens on the same location, but the order is changed, then the loading is happening after storing. So, store will write a new value and that is what the load is doing. So, the load is before the store in program order and interchanging of the result will result inside a wow hazard. Similarly, if the store is before the load in the program order, so that is what you can see, there is a store and a load. So, the interchanging will result inside a raw hazard. So, we have to be very careful when you interchange the order of load and store, provided they are going to access into different, provided they are going to access to the same address. As mentioned in the first point, load and store can be safely done out of order. You can exchange the order provided they are going to access different locations. So, in this example what is being mentioned, if the location where this load and store going to access, if they are different, interchanging of the order is no longer going to be a problem. So, interchanging two stores to the same address can result inside a wow hazard as well. Now, to allow a load and a store to interchange their order and execution, you have to perform a speciality check. And what is the checking all about? To determine if a load can be executed at a given time, the processor can check whether any uncompleted store that precedes the load in program order share the same data memory address as that of the load. Meaning, suppose if I wanted to run a load instruction now, processor has to check any store operation that is before this load is still under execution. So, all uncompleted store that precedes the load which having the same address. If the address is not same, it is not at all a botheration. Similarly, a store must wait until there are no unexecuted loads or stores that are earlier in the program order that change the shared memory address. So when you are going to deal with loads and stores, any kind of interchange in the order in which they are executed, you have to take care of two things. Point number one, if you wanted to put a load instruction somewhere, processor has to make sure that there are no uncompleted stores before this load instruction which are operating on the same address. Similarly, a store cannot happen at a point until all previous uncompleted loads or stores which are pending. So as long as you have pending loads and stores, a store instruction cannot come there with the same address. So if this checking is being properly done, exchange of load and store can be fairly easily managed. Now coming to hardware based speculation, let us try to see what speculation is. Whatever control hazard that we have discussed now, how can you do or solve it in Tomasulo's approach? The technique is called speculation. Speculation means fetch, issue and execute instruction as if branch predictions are always correct. But branch predictions can go wrong. So you should commit the results only if the prediction was correct. So there are two approaches, or basically there are two things that we have to keep in mind when you go for speculation. You should have a mechanism wherein you can fetch, decode and execute instructions as per the directions given by a branch predictor. But if the prediction happened to be wrong, you should have mechanism to revert back whatever actions you have done, or you should commit operations only if branch prediction is correct. So you require additional circuitry in the conventional Tomasulo's algorithm, which has reservation stations, which has register status indicator and which has common data bus that is been connecting to the registers and reservation station. Extra circuitry is required to have a check on these 2 points that we discussed right now. So what do you mean by instruction commit? Instruction commit means allowing an instruction to update the register or memory only when instruction is no longer speculative. So think of a date. When are you going to update a register? When you have a load operation or when you have an ALU operation where the result is to be returned to a register. Similarly, when you have a memory operation like store operation, you are going to update the memory. These updation in registers and memory should happen only when the instructions are no longer speculative. So when you run a speculative instruction, what do you mean by a speculative instruction? When I am going to run a load instruction which is being predicted by a branch predictor. The branch predictor tells that you can run the loop. Let's say the first instruction in the loop is a load instruction. So you are going to run this load instruction as per directions given by the branch predictor. So at that point of time, this load instruction is a speculative instruction, meaning I am not sure whether it's must execute or not. Branch predictor tells that you can execute. But let us assume that after few cycles, the condition of the branch is now no longer speculative, means we know what is the outcome of the branch. And if the predictor was correct, at that point of time, the load instruction is no longer speculative. So certain instructions which come as a follow through of a branch or as a target of a branch, for some time they are speculative instructions when you run and execute. So essentially what we do is, we run these instructions, store the result in some temporary place. When you come to know that these instructions are no longer speculative or the outcome of the previous branch is known and you are sure that these instructions are to be executed, whatever is the result of these instructions which were stored in a temporary place can now update the corresponding register and memory, and that is the core idea behind speculative execution. We need additional hardware to prevent any irrevocable action until an instruction commit, and that extra hardware is known as reorder buffer, also known as ROB. ROB holds the result of instruction from completion to commit. So when you perform a speculative operation, You will do the operation, get the result, stored in a place called reorder buffer, and when you come to know that this instruction is no longer speculative, from the reorder buffer copy it into memory or to the registers. So now there is a small modification in the reservation station. Operand source is now reorder buffer entry instead of the functional unit. So previously you are actually waiting for the functional unit to produce the result. So you are pinging the CDB, the common data bus, waiting for a result produced by the execution unit 1 or execution unit 2. Now we are not pinging the CDB by looking at the number of execution unit. We are pinging the CDB by looking at the reorder buffer entry that is to be put. The difference is, with speculative execution, when you produce a result, rather than telling execution unit 1 produce the result, the change is the result that is to be generated by this functional unit has to go to reorder buffer entry 2. So everybody who is waiting for reorder buffer entry 2 can appropriately get them. Hardware based speculation needs 3 techniques. You need to have a dynamic branch predictor which will tell you which instruction to fetch and execute. You need to permit speculation to allow execution of instructions before the control dependents are resolved. Control dependents are resolved means before the branch outcome is known. At the same time, you need to have an ability to undo if whatever speculation is going wrong. And then capability for dynamic scheduling to deal with scheduling of different combination of basic blocks. Overall, we are allowing an instruction to execute and bypass its result to other instructions and prevent an instruction to perform any updates on writing in register or memory until the instruction is no longer speculative. Now let us try to look into what is the structure of reorder buffer. So reorder buffer is basically the extra hardware. It is a queue which has 4 fields. It will store the instruction type, the destination field. If you have the reorder buffer to which the outcome of execution units is going to come, we have to tell the value of R1 is going to be 4. So R1 value is entered and 4 is entered, meaning an instruction produces a result which has to be updated in register R1 and the content value is 4. Actual registering of R1 will happen only when this instruction is no longer speculative. So when an instruction is in a speculative stage, I store the result in reorder buffer, and reorder buffer is a temporary register which will store the value or the outcome of an instruction before commit stage but after complete stage. That is called a value field. And then it will also tell a status whether the instruction is issued only or it is completed. Register values and memory values are not written into the registers and memory until an instruction commit. So as and when the instruction commit, there is a copying that happens from reorder buffer into registers and reorder buffer into memory. Now what happens if you are having a misprediction? Speculated entries are only, so the result of the executed, the speculative instructions that are executed are available only in the reorder buffer. I can just flush off the corresponding reorder buffer entries. So even if you execute a speculative instruction, the result is available only in the reorder buffer. The result is not updating your memory or registers. So any kind of misprediction that happens, it's only clearing of reorder buffer. No memory or register contents are being updated with wrong results. So this diagram tells, on the left side we can see the conventional Thomas-Ulos algorithm where speculative execution is not permitted, and on the right side we have Thomas-Ulos algorithm with a reorder buffer entry. So what is the basic change? Here you can see there is a reorder buffer. So the outcome of the execution which is written into common data bus, now it is not going into floating point registers, it is coming to this reorder buffer. Now from the reorder buffer, the moment you come to know that an instruction is complete, if it is a store operation, you are going to update in the memory. If it is an ALU operation where the registers are updated, then it happens. So from the reorder buffer, you update memory if it is a store operation, or you are going to update the register file if it is an instruction wherein the result is returned to registers. So the store buffer concept which was there is not here, you have only load buffers. Now what are the operations with the reorder buffer? First is the issue operation, execute operation, write result operation, or it is also known as complete operation, and the last stage is called commit operation. Let us see each one in detail. So what is issue? So when you deal with an issue operation, you have to get an instruction from the instruction queue. Once you get the instruction from the queue, issue the instruction if there is an empty reservation station and an empty slot in reorder buffer. This is the new extra point. So the issue operation in a speculative execution is slightly different. I need to check for two entries. Do I have a space in the reservation station associated with the operation? Let's say my operation is multiplication. I have to check whether there is an entry free in the reservation station of multiplier. If so, I have a space there. Second, if my multiplication is over, do I have a space in the reorder buffer where I can temporarily store the result? So I am pre-booking a slot in the reorder buffer and I will get a number. Okay, your number is reorder buffer number 10. So I will tell you whatever is the result that is been done by the multiplier unit, kindly write into slot number 10 in reorder buffer. So two things are needed, an entry in the reservation station and an entry in the reorder buffer, and the entry in the reorder buffer is used to tag the result. Any output that is produced by a functional unit has to be written to reorder buffer directly, not to register file, and when you write, you should know where to write, and that is what is called the entry in the reorder buffer. So you have to get a slot number or tag from the reorder buffer for every instruction and send the operands to the reservation station if they are available, either in the register file or in the reorder buffer. If you are taking a value from the reorder buffer, then it is called a speculative register read. If the value is no longer available in the reorder buffer, then you can go and take it from the register file. The number of reorder buffer entry is also sent to the reservation station to tag the result. So that's why whatever is the value that you get, the reorder buffer entry, that is also added into the reservation station such that at the end of the operation, the result is forwarded to the appropriate reorder buffer entry. If either all reservation stations are full or if the reorder buffer is full, then instruction issue is stalled. So once the issue is stalled, all other pending instructions are also stalled because issue should happen in order. So what about execute? If one or more of operands is not yet available, then you have to monitor CDB waiting for the value. When both operands are available at a reservation station, you perform the execution of the operation. Instruction may take multiple clock cycles in the stage and load still require two steps. One is address computation and one is accessing memory. Stores need to have base register value available to perform execute because address calculation has to be done. And what will you do with the write result? In the write result, when the result is available, you have to write into CDB. Here is the difference. You write into CDB with reorder buffer entry. Let us say ALU1 that is going to produce a result. In previous algorithm, in the naive Tomasulo algorithm, we are telling ALU1 produced a result X. And now the difference is X is the value produced and that has to be written to reorder buffer entry 5. So rather than telling which functional unit produced the result, it is going to tell you what is the reorder buffer entry. So data in CDB will go to this reorder buffer entry that has been mentioned and to reservation station waiting for the result. If the value to be stored is available, it is written to the value field of the reorder buffer entry for the store. If the address for the store is available, then you will store the address portion in the reorder buffer. If the value to be stored is not yet available yet, the CDB must be monitored until that value is broadcasted, at which time the value field of the reorder buffer entry of the store is updated. Now let us look into this additional last stage called commit. So in commit stage, it's a final stage of an instruction after which only its result remains. So once if an instruction is committed, meaning the memory or the registers are updated, you cannot revoke this action anymore. So commit happens only if you are sure that an instruction is no longer speculative. So all instructions which are executed, hoping that they will happen based upon the outcome of the branch predictor, the result of all these instructions will be temporarily stored in the reorder buffer. As and when you come to know that these instructions are no longer speculative, means the outcome of branch is known and whatever you have run is really required, then transfer the contents from reorder buffer into memory or registers. And there are different sequence of action that you have to do for a commit operation. If it is a branch instruction, you have to do certain things. If it is a store operation, you have to do certain things, or if it is any other operation, that is also what you have to do. The normal commit case occur when an instruction reaches the head of reorder buffer and its result is present in the buffer. The processor updates the register file with the result and remove it from reorder buffer. So consider, let me draw the reorder buffer here. So let us say the reorder buffer numbers 0, 1, 2, 3, 4, 5. Now imagine a case where your reorder buffer entry 3, that value you got, let us say 5. And then you got the reorder buffer entry where you are telling you have to write something into R2 and the value is 8. Then 6th instruction, then the 4th instruction is getting complete. It is telling you have to write some value to location 2000 as 10. And then you got a value that is there, R5 equal to 10. Now the very first entry in the reorder buffer, that is now complete. That means this instruction is committed. Once that is committed, this is committed. But I cannot commit your R15 because that has not yet reached the front of the reorder buffer. So an instruction will get committed only if that instruction reaches the head of reorder buffer that is been mentioned over here. So all instructions 3, 4, 5, etc. will be there in reorder buffer until you get the value that is available for the reorder buffer entry 2, because commit always happens in order. This is the program order. Commit happens always in order. Committing a store is similar to, except what is been mentioned, rather than writing into registers, now you are going to update the memory. And what will happen when it is a branch instruction? When I have a branch with the incorrect prediction reaches the head of reorder buffer, it indicates that speculation was wrong. Then the reorder buffer entry is flushed and execution is restarted at the correct successor of the branch. So the moment you come to know that your branch instruction was having an incorrect prediction, flush out all entries, flush out all speculative instructions. If the branch is correctly predicted, the branch is considered to be finished. So we had a quick glimpse of how the concept of speculative execution happens. So additional control circuitries and storages are required on conventional Tomasulo's algorithm so as to improve it to speculative execution. We learned about concept of reorder buffers, and reorder buffer is a place where values of speculative instructions are being temporarily stored, and during commit, commit is always in order. So when you look into the concept of dynamic scheduling, you fetch in order, decode in order, issue in order, execute out of order, complete result out of order, but commit in order. That is the order in which things are been happening. So with this we come to the end of lecture number 10, which talks about hardware based speculation. Thank you.